Hello, everyone. It's really nice to present a conformal prediction in front of the inventors. Yeah, I feel very honored. So today I'm going to present synergy conformal prediction. It is a joint work with Ola Spjuth. So I'll start with a small introduction. So usually large and distributed data sets pose many challenges for machine learning. In case of, the large data, it has to be, it's really difficult to train it at once. So it has to be partitioned into chunks, or when the data is distributed, it has to be pooled. So in our approach, like in case of distributed, using synergy conformal prediction, the pooling can be avoided, and it can work in small chunks, and the results can be combined from conformal predictors using synergy rules. It's a really promising approach, and we demonstrate it for classification problems. So I will briefly tell about what was there in synergy of monotonic rules. So our paper is basically, we got motivated from this paper, a synergy of monotonic rules, which was by Vapnik and et al. So in this paper, the authors have combined the estimated conditional probabilities to construct the optimal synergy rules for different pattern recognition problems. So basically, the conditional probabilities are the monotonic functions. When combined, it gives another, the monotonic measure. So we'll discuss it in later slides. So I'll briefly give a background on what is a classification problem, and we'll set some notations, which I'll be using in later slides. So in classical classification setting, we are given L data points. Let's say we will call it Z, and Z1 to ZL are the data points we have, and we'll call it examples, and each example, Zi, consists of xi and yi. Xi, we can view it as a feature set, or we can call it object. And yi's are labeled, it's label, it can be class label, like class 0, 1, or it can be anything, but we'll call it class 0, we'll give it a number, class 0 to class k. And given this L data points, and we want to predict the label of a new object, x new. So we just know for the new object, its feature set, and its label is unknown. And for example, the widely used machine learning algorithms for classifications are support vector machines and random forests, etc. Conformal prediction is basically, it complements the prediction made by machine learning algorithms with a measure of confidence in the form of prediction interval at a user-specified significance level epsilon. In classification case and for binary classification example, this prediction set can consist of just one class 0 or class 1, or it can have both the class, and or it can be null. And for regression, it gives some interval. And validity of conformal predictors are theoretically proven, and it assumes data is exchangeable. So I'll now introduce conformity measure and conformity score. So in conformal setting, prediction setting, a conformity measure is a way of measuring the closeness of an example in relation to the previously seen examples. And the efficiency of the conformal predictor depends on the conformity measure and the choice of epsilon. In our example, in our experiment, we used calibrated conditional probability as conformity measure. And I'll talk about it in details in a couple of slides. So in this conformity measure, or it's a class conditional probability, a calibrated conditional probability, where this fx is a prediction rule of the model and trained on the training data, which was trained on the training data, and this y corresponds to the class labels. And yeah. And in conformal prediction settings, the following are the two main approaches, and they can be used for both classification and regression problems. The transductive conformal prediction requires retraining of the model for every test example. Whereas in inductive conformal prediction, a subset of training examples are set aside as a calibration set, and predictions can be made without retraining the models. Our method is based on inductive conformal predictors, so I'll tell ICP in a bit detail. So in ICP, let's consider we have training data, we call it Z, and we first divide it into a proper training set and a calibration set. And suppose there is a method, a function called ZT, which takes training data and some example. It is used to measure how well the example XY conforms to the proper training set ZT. Yeah, as I showed previously, like this can be our, in our experiment, we consider this measure to be a calibrated conditional probability. And the predictive model trained on the proper training set ZT is used to compute the conformity scores for the calibration set. And let X nu be the example we want to predict, and let alpha nu y be its conformity scores computed using the same function, same conformity measure. Then the ICP p-values are computed as, I think you might have seen it in other presentations also. We just saw it in previous presentation. So here the y corresponds to the class labels, and index j corresponds to, I mean, that belongs to that particular class. So we consider the class-wise partition, and this tau is a random number between 0 and 1. So once we have these conformity scores computed for all the calibration examples, the examples in calibration set, and for the example we want to predict, then we compute the set predictor is computed, the inductive conformal predictor corresponding to the tuple, this conformal calibration set, and this the rule, the conformity measure is defined as a set predictor, which is like which corresponds to the epsilon, and it considers the class, those class for which the p-value, the corresponding p-value is greater than epsilon, and this epsilon is a chosen significance level, and usually 1 minus epsilon is known as a confidence level. And we'll talk about different ensembles of conformal predictors, and they were introduced to I mean, the ICP, in ICP we keep aside a set of data for calibration set, and so it's kind of, we are losing some information. To overcome that, the drawback in ICP, the ensembles of conformal predictors were introduced. For example, cross-conformal prediction and aggregated conformal prediction. And in these ensemble methods basically aggregates the resulting p-values. And usually they are not guaranteed to be valid because the combined p-value need not be uniformly distributed. The validity of TCP and ICP is proven in that they produce 1 minus epsilon expectation tolerance regions, where epsilon is the selected significance level. However, the validity of ensembles of CPs has not been theoretically proven, and it has been discussed in these papers. So we propose synergy conformal prediction to address the validity problem of ensembles of conformal predictors that combines monotonic conformity scores instead of p-values. So SCP is originally inspired by synergy of monotonic rules by Wapnick et al. And the SCP method differs from most of the other ensemble methods discussed previously, in that SCP combines conformity scores rather than combining the conformal p-values or prediction intervals. Yeah, so a given training set, and we assume that it is drawn from an exchangeable distribution P. The training data is first divided into a proper training set and a calibration set, and like ICP, yeah. Then the proper training set is further divided into M non-empty disjoint subsets, and each subset, ZTM, where a small m ranges over 1 to capital M, is then used for training. And we have M predictive models trained on the individual partitions. And then they are used to compute the conformity scores for the calibration set. And let's denote them alpha mj, where m corresponds to the 1 to m and individual partitions, and j corresponds to the index of the calibration set. Yeah. And for each class, we compute this conformity score. And yeah, FMXJ is the prediction rule defined by the predictive model trained on the mth part of the training set. And then we aggregate the conformity score across models. And it's defined as the average of all the conformity score across different models. And let's say X nu is the example we want to predict. So we also compute the alpha nu, and we first compute the conformity score against each model, and then we aggregate it across models. And then similarly, the p-values, like we saw in ICP, is similarly this p-value is computed for this example we want to predict. Yeah, so for our experiment, this is the design of experiment. So given a data set, we first partition it into a training set and a test set. And the training set is further divided into proper training set and calibration set. And the proper training set is further divided into M partitions. We call it, let's split 1 to split M. And on each model, each partition, we train a model. And for each example in calibration set, we compute the conformity score using these model. And also for the test set, we compute the score, and then we finally compute the synergy conformal p-value. So yeah, as I just explained, the proper training set is randomly partitioned into m equal parts, and a model is trained on each part, and we use basically 3 machine learning algorithms. Support vector machine using the linear kernel, and support vector machine using RBF kernel and random forest. And hyperparameters for these models are used using 5-fold cross validation. And all the experiments were repeated 30 times. And we use observed fuzziness as a measure of efficiency, which is defined as the sum of all p-values for the incorrect class labels, and lower value is advantageous. In the first experiment, so in this figure, so in most of our experiments, we divide a proper training set into three parts. So here M is 3 in most of our examples. So in first experiment, the proper training set is divided into 3 parts, and the same machine learning algorithm was applied on each individual part. And in the first set, we applied linear SVM on each individual partition, and the first column corresponds to from the partitions, the best, which has the best efficiency. Yeah, so we didn't report all the 3 results from all the 3 partitions, but the best one, which has the lower value, which is the best among partitions. And the ICP corresponds to the ICP trained on the whole proper training set, so when it is not partitioned. And the SCP corresponds to the synergy of those 3 small partitions. And similar it is when we used RBF SVM. And for most of the cases, the SCP is better than each individual ICPs, the small ICPs. Yes, of course, the ICP is the best. In this second experiment, so for all our experiments, we used confidence level 95% and 3 partitions. So in the second experiment, it's similar to first experiment, but instead we applied 3 different machine learning algorithms for 3 different partitions. So on the first partition, we used linear SVM, and the second RF, and the third we applied RBF SVM. And in this we reported the efficiency of each small partition ICPs, and for most of them, like the SCP, the synergy of these 3 is better than each individual. And in the third experiment, we don't partition the data. We didn't partition the proper training set. Instead, we applied 3 machine learning algorithms in turn on the same data. And we call it ICP because we are not partitioning, so it is same as ICP. So it's SVM ICP, RBF ICP, and RF ICP and RBF SVM ICP on the same data. It was applied, and the synergy of these 3 were computed as SCP. And similarly, we computed the CCP using 3 different machine learning algorithms. So this was our third experiment. And this is like the measure, the comparison of efficiency for the experiments we just discussed. So yes, ICP is best, and the SCP is better among all the partitions. And in the fourth experiment, we compared calibration of SCP with ICP and CCP. And for this, we have very poor model, RF with 10 trees. And with this poor model, the CCP is not, I mean, it doesn't calibrate well. So it's kind of not valid, seems not to be valid. And whereas ICP and SCP are still valid. And in the fifth experiment, we compared the running time of ICP, SCP, and CCP. And the SCP seems to be faster. So in conclusion, SCP produces valid prediction intervals for a new object. And yeah, it doesn't reach ICP level of efficiency on partition data. But in most cases, it is better than each individual best partition. And computations can be parallelized and reduce need for data pooling, or it allows for partitioning the data, the large data. And it is attractive for distributed and federated settings. And because we don't have to share any model or data, it's just like we, in case of federated setting, we just need to share the conformity score. So, I mean, it works best. Hopefully it will work better. It suits for federated settings better. Thank you.